Hello, hello, hello. How you doing? I hope you're doing okay. I am doing fine. And shall we make a math video? Why? Why not? Right? So a friend of mine sent me a question about a week ago. She asked, I'm talking here with a few friends and we're discussing like can infinities be multiplied? For example, between 0 and 1 there are infinite numbers. And between 0 and 2, are there two infinite numbers? Is it the same amount? So I answered her question. But to go into that, I had to go through a few little steps, which I'm going to talk about here. Infinities, they don't usually work. They don't always work the same way that they do with like finite things that end. But some things work the same way. But in this case, let's talk about how counting worked. So when you first started learning how to count, you were very small. Someone said, like, let's say you were going to count coins. So you had like a few coins there. And someone taught you, there are these numbers 1, 2, 3, 4, 5. You're going to do like 1, 2, 3, 4, 5, 6, 7, which means there's 7 coins, right? So what you're actually doing here, mathematically speaking, is that you're making a relationship with this set of things with another set that you know how many elements there are, right? Which we use the counting numbers, which are 1, 2, 3, 4, 5, 6, 7. And what you're doing here, you're doing a relationship, a one-to-one relationship between the elements of this group and the elements of this group. One-to-one because each one member here is going to go to one member in this group, right? So we're going to have this one goes to this one will be 1, this one will be 2, this one will be 3, this one will be 4, this one will be 5, this will be 6, this will be 7. It doesn't really matter which one is which, right? I could have this one be 1 or this one could have been 7. It still doesn't matter. We're matching them, right? And no one here is alone, and no one here is alone. No one here has 2 buddies on this team, on this group, right? No one here has 2 buddies on here. So we can say that they have the same number of elements. And since we know here, by the way counting numbers works, we could go all the way to 7. It means there's 7 elements. So this group has 7 elements. Of course, you as a little child didn't think about all this one-to-oneing, right? Someone just said, you do that. Very often kids will go like 1, 2, 3, 4, 5, 6, 7, 8, 9. So there are 9. And then you have to go like, no. You can only touch one coin one time, right? And sometimes they'll go 1, 2, 3, 4, and then they're done. I'm like, no, but you forgot all these 3, right? So that's kind of the way we're going to think about, counting, right? So when we're doing this, this is what we do when we have finite groups, right? And it's very similar to what happens when we do with infinite sets, right? So let's clear this. Clear. Okay, so let's say we have the counting numbers 2, 3, 4, 5, 6, and they keep going forever and ever. If you give me a number, I can give you a bigger number, right? So we know these are infinite. There is no biggest counting number, right? If you give me 1,000, I'll say 1,001. There's no biggest number. And let's compare them to the counting numbers plus 0, right? Which are the natural numbers. So we'll have 0, 1, 2, 3, 4, 5, and they keep going, right? Also, counting numbers and natural numbers. Natural numbers, if you give me a number, I can give you a bigger number. There is no biggest number. They're infinite, right? Okay, so what we want to do here is to see if they're the same size, we want to find a one-to-one mapping, right? It's this relationship we're trying to create is a mapping of the elements in this group with the elements in this group, right? So let's try a mapping here. I'm going to do red because spoiler alert, it's not going to work. Let's try a mapping here that every element in this group will be matched to the same element in this group, right? So if we do that matching, 1 goes to 1, 2 goes to 2, 3 goes to 3, 4 goes to 4, 5 goes to 5, 6 goes to, well, 6 is here somewhere. This mapping, everyone here in this group will have a buddy, and only one buddy. Everyone here, no, 0 doesn't have a buddy. So this mapping doesn't work to show that they have the same size. right? But that's okay. There are other mappings we can try. Let's go back, take away this. All right, let's try this other mapping. Blue, because it's going to work this time. Let's say every element in this group, we're going to match to the element that's one smaller on this group, right? So it's already lined up, so that helps, right? Convenience. Convenience is very useful in math here, right? We want a convenient mapping so that it shows. So one smaller than 1 is going to be 0, 1 smaller than 2 is going to be 1, 1 smaller than 3 is going to be this, 4 goes to 5 goes to 6 goes to 5, right? Will everyone in this group have a buddy in this group? Yeah, because you can always find one smaller, right? They're always going to be in here, right? And will everyone in this group have a buddy in here? Well, yeah, because we can always find one that's one bigger. If I say 1,000, yeah, 1,001's going to be in this group. So we could have that matching. Will anyone have 2 buddies? Like, will anyone in here have 2 in here that it matches to? No, because there's only one number that's going to be one smaller, right? So if I say 17, there's only 16 that'll work here, right? And the same goes the other way. So this is a mapping that works, right? And that means that these 2 sets have the same amount of elements. It's infinite, but it's the same kind of infinite, right? Which is strange. It kind of blows minds a bit, because if you think about it, like we tried to do the first mapping, every single element in this one is in here, and yet we have one more element and they're still the same size. Yeah, because that's where infinite numbers, infinite sets, and finite sets are different, right? Can't use always the same way of thinking, but we're thinking what is counting, and this is how we count, right? We could also do another mapping to another set. Let's think about the even numbers, right? So 2, 4, 6, 8, 10, 12. They also are infinite, right? If you give me an even number, I can give you a bigger even number. If you say 1,002, I'll say, well, 1,004 is also an even number and it's bigger. Also infinite. Can we do a mapping that goes from this set to this set, following all the rules we have for counting mappings, right? 1 to 1, only nothing left in either group. We have one which is pretty it's pretty straightforward, just because we can think about the idea of what is an even number, right? It's one number that can be divided by 2. So we could just do a mapping of everyone in this group. We're going to take double of it, and it's going to be in this group. So we can match 1 goes to 2, because it's double of it. 2 goes to 4. 3 goes to 6. And so on, right? 5 goes to 10. 6 goes to 12. Right. Great. Anyone in this group not going to have a buddy here? No. Anyone we get here, 500. Double of it, 1,000. It's going to be in here, right? Anything I get in here, can I get half of it? Yes. So if I get here 700, can I find half of it? Yeah, 350 is going to be in here. Everyone has a buddy. Anyone have 2 buddies? No, there are not 2 answers for double of a number, right? If I'm doubling the number, I'm going to have only 1 answer. And there's same the other way around, right? If I take half of a number, there's only 1 answer I can find here. So this is a good mapping. It works. And it also like blows minds, because if you think about it, every single element in here is in here, right? They're here. They're the even numbers. And yet we have all of these odd numbers in here also, but these 2 sets are the same size. They're both infinite, and they're the same size, right? It is like mind-blowing here. You can do mappings for other sets that don't seem like they'd have the same number of elements, but they do. So the integers, for example, let me clear this because we need more space. Space for math. So let's compare so we have the natural numbers, because I like having the 0. And if you don't like 0, I'm sorry. So let's compare them to the integers, right? The integers have the 0, and then they have the -1 and the 1, -2 and 2, -3, and this so on. So we can do a mapping here also, and that'll show 0 goes to 0, and then every odd number is going to go to a negative, and every even number is going to go to a positive. We could do a mapping this way, they would all match. No one will be left alone here. No one would be left alone here. No one would be matching to 2. It's a little annoying to write, but you can always write this, right? Formally writing it, but the idea is there and we can see it. You can even do a matching of the natural numbers to the rational numbers. That's a bit more annoying, like all the fractions. That's a bit more annoying and it takes some time, so I'm not going to do it here, but it can be done. What can't be done is from the natural numbers to the real numbers, right? That have square root of 2 also, that have pi, right? They're all these weird numbers, irrational. Shouldn't have called them weird, but yeah, so, but that's not exactly what my friend asked, right? What my friend had asked was not with just natural numbers. She was asking about the numbers between 0 and 1 and between 0 and 2. So it's clear again, but we can already see that it requires a bit of care, right? So between 0 and 1, there are infinite numbers, right? And between 0 and 2, there are infinite numbers also. If we were to think of this, we want to think of it, are they the same size? We try to create a mapping, right? That's what we're going to do. Even though these cannot be mapped to the natural numbers, we're going to see if this one can be matched to this one, right? So the mapping I'm going to do is 0 goes to 0, and I'm going to do 1 goes to 2, because I want the beginning and the end. Again, convenience, because you can always do another mapping and it doesn't work like we tried when we included the 0 to the counting numbers. But we just need to find one mapping that works, right? So such is math. It's kind of weird. So I want to do a mapping here that's very similar to what we did when we were doing even numbers, which is let's get double, right? So if I had, for example, half here, I'm going to take it to where 1 is here, right? And then if I had 1/8 here, I'm going to take it to where 1/4 is here. It's going to be about here, right? This is where it's going to map. So now we have to think, like we have this idea of how we're going to map. Let's think if it works with all the rules we have, right? Well, everyone in here have a buddy in here. Well, if we think of any number that we'd get here, double of it will stay in this space, right? We can find it here because nothing is going to be bigger than 1. So no doubles are going to be bigger than 2 and no doubles are going to be smaller than 0, right? Everything is here. Can we do the other way around? Will everyone in here have a buddy in here? Well, if I choose a weird number, I like choosing weird numbers. No, let's try starting with a not weird number. If we try with 1.5 here, if we were to get 1.5, half of it is going to be 3/4, right? 3/4 is in here. Look at that. We can find a match, and there's only one match for it, right? It's great. If we were to try to find for the square root of 2, which is around here, if we wanted to try to find half of it, we can find half of it is going to be square root of 2 over 2. And there's only one possible answer, right? So there's only one possible answer. No one in here is going to miss a buddy. No one in here is going to miss a buddy. No one has 2 buddies. So it means that these 2 sets have the same size. Even though, again, mind-blowing, because every single number in here is just in here, and yet we still have all of these. But, crazy enough, here we go with math again. These 2 sets have the same amount of numbers. It's an infinite that's bigger than the natural numbers, but these are the same size, and that is how we count infinities. We compare sets that we know to see if they're the same size, right? So, as my friend said, if we're doubling in the sense of taking double of this, if we're multiplying infinities in the sense of I can take double of this and see if they're the same size or not, well, they are the same size, right? And if we add an element, we found out when we were doing with the natural numbers and adding the 0, it's also still the same infinity, right? So I hope you enjoyed this. I did. I always do. Crazy math is what I like. Let me know if you have any questions. Sometimes it takes a little while for this to sink in. And sometimes, you're in the shower, you're thinking about life, and you're like, ah! Sometimes it takes 4 showers. It's okay. Sometimes it takes a while. Sometimes it doesn't sink in, but that's okay. Just thinking about it starts making our heads turn, thinking about different things. Math is culture, right? Yeah. Hope you guys enjoyed it. Bye.